Hi, everyone. Welcome to this week's seminar. We're excited to have Dr. Yuri Rzhanov speak about his research. Some background on him: he received his PhD in semiconductor physics from the Russian Academy of Sciences, and before joining UNH as a research professor, he worked at Heriot-Watt University in Scotland, and his research interests span optical methods for seafloor mapping, photomosaics, and also sea bottom reconstruction. So I'll hand it over to you.
Thank you. Good afternoon, everyone. And I hope that everyone looked up this weird Greek word, boustrophedonic. But just in case somebody didn't, I'll tell you that it's simply a lawnmower pattern, which is shown up there in the picture. So just imagine that the ancient Greeks were mowing their grass, and somebody would ask the neighbor, "Hey, Achilles, have you been boustrophedonic today?" or something like that. Well, anyway, back to the title. The medieval Denmark was a great maritime power. And obviously, they had to do a lot of underwater video surveys. And so the prince was in charge of that, and in addition to other responsibilities. And he asked himself this question probably many times. And so we, with MacLean, tried to answer this question and show that there is an alternative to this approach, which existed for many years. So this is classical, typical boustrophedonic survey pattern, which has been designed for a drone. So drone has GPS, so it has very good positioning. So it starts here and goes in these straight lines. And so this is a frontal overlap, this is a side overlap, but we have our own argo for that. So we call this sequential link, because we know that there is overlap. And we call that cross-link or non-sequential, because we hope that there is an overlap, but we actually don't know if there is, and if there is, we have to find it. So what happens is that a typical video survey, and suddenly there is a gap, and they had no idea that they had a gap before they actually processed the data. So why is that? First of all, narrow swath due to poor visibility. So you have to look at very small area on the sea bottom because it's underwater. And second, because again of being underwater, you do not have a reliable positioning system. You don't have GPS. So there were proposed improvements to that. And these improvements are based on the concept which was proposed, which is called SLAM. It's simultaneous localization and mapping. And it reduces the accumulation of errors. So when you move and you rely only on the previous step, then the errors are accumulating. But if you are lucky enough to get back to the area where you already have been, then you can use SLAM and redistribute the errors and get better result. So this is, again, the example of the proposed improvement in 2010. So you start here and go in one direction, then in another direction, and everything is great, it seems. So, but do we really have to stay boustrophedonic? So we proposed the following very simple system. So there is a motor which moves linearly, and it has rotational arms which are rotating with cameras at the ends. So what does it give us? First of all, it's really difficult to give any numerical estimates because there are so many parameters which are involved. So it's the camera altitude, which typically changes within 2 or 10 meters. It's a vertical field of view of camera, which is again in this range. Rotational speed, how fast these arms rotate. Number of cameras, doesn't have to be 2, it could be 1, or it could be 6. Instead of these arms, there could be a disc, for example, with many cameras on the side of the disc. So the best estimate that we can do is to provide a lower bound estimate for linear speed. So if we move linearly with speed lower than that, then we are guaranteed not to have gaps. Just guaranteed. Okay, now that's the result of the simulation. So the motor is moving in a straight line, and 2 cameras are, one is blue and another is red, and obviously they are rotating. So this is more interesting graph. So this is the coverage, because each snapshot is rectangular. So if we overlap them and calculate number of times that different frames hit every spot in the area, we'll get something like that, where black is no coverage because it's outside the swath. Blue is a relatively low coverage, red higher, and yellow is the very high coverage. So what sort of values are these? So suppose we are moving with the very high speed. Linear speed is 30. Well, I'm talking about simulation. So these 30 do not mean anything specific. But suppose we are using like linear speed 30. So you can see that the distribution of the coverage is almost Gaussian, and on average, every area is hit, well, about 2-3 times. So when we start moving slower, linear speed 20, it still is a Gaussian, but coverage gets higher. On average, it's like around 4. So, and finally, if we start moving even slower, then this dependence becomes a little bit more complicated, but complicated because the coverage consists of rectangles. Rectangles which are superimposed, and they are rotated, they are shifted, etc. So that's why it has this funny shape, but you can see that the coverage, average coverage gets closer to like 8. That's just to show an example. So I call it the road to Calvary, because we had many problems in front of us. So we didn't have ROV, AUV, SUV, or anything like it. So we used bridge over the wave tank because it was moving. We knew that it's moving slowly and with a constant speed. So we can use it as a sort of proxy for AUV. We didn't have cameras, but we could borrow it from Jan Dijkstra. We had no motor. We borrowed it from Tom Weber. We had no idea how to build the device, but we had Mike Tuttle. So fortunately, we overcame all these issues, and here it is. The experiment started. So actually, McLean, who is here, did all the experiment alone without me, because I was the project was postponing and postponing all the time, and finally the time of my vacation came, and so I left, and when I came back, McLean said, "I've done everything. So all I had to do is to process the data." So to explain what is that, I say these are cameras. that's rotating arms. That's a motor. And okay, that's probably not needed, but just in case, you know. So we had to use something unique pattern to create a mosaic. Because if you are looking at the wall, there are no features at all. So we have no idea how to combine two images. So the images should have some texture, some unique texture to be able to register one image with respect to another. So we were discussing various options, and that's what we finished with. This is the orange fencing, and McLean painted it with pseudo-random spots, black and white. You cannot see white here, but there will be. So when I looked at the paintings, I thought, okay, we have to figure out if it's enough unique to make a mosaic. So I took my phone and click, 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 and it worked. So I thought, okay, fine. We have enough sufficiently unique pattern to try to create a mosaic. So we, I took the footage that McLean took and did the sequential registration between frames. And oh no, it was absolutely ridiculous. But I knew what was going on. So the thing is that if the camera is not looking completely perpendicularly to the target, it's not normal, then there is always some distortions which accumulate, and then things go wrong. So sometimes it's called smile distortion, sometimes frown distortion, sometimes perspective distortion, doesn't matter. We have them all. So that's why this is the frame 0, 1, 2, 3, etc. And it's no big deal to process it, to make it look right. So because it's only sequential links and slightly oblique camera, and camera is always slightly oblique, whatever you do, because even if it's completely vertical, the pattern you are looking at could be at a slope. So, and that is the result when we added cross links and applied SLAM. So this green stuff is sequential links, and this blue are cross links. So links with frames with significantly different numbers. So, right, okay, this, I just like this image, it doesn't tell you anything, but these are outlines of the footprints, how they are like creating this nice pattern. And this is a mosaic, resulting mosaic, which is almost perfect. It has, difficulties only near this edge, and frankly, I think that it's due to some, it was not completely flat. And the distance between the camera and the target it was looking at was pretty small. To have a, if you are looking, you can make a mosaic from a completely flat surface, but to consider it flat, you have to be like 20 times higher than the changes in height. So we obviously did not satisfy this criteria, but nevertheless, it's almost perfect mosaic. So what are the advantages of this non-boustrophonic approach? First of all, arbitrarily wide swath. You want to have mile? You can have mile. salesman. You probably won't find a motor which will move these mile-long arms, but that's a different problem. In principle, you may have a mile-long arms. Second, it relaxes constraints on overlap if you have to add to this. If the swath you can do is not enough for you, you can still add the boustrophedonic pattern to it. And as it is very wide, it relaxes the constraints on positioning system a lot. And finally, last but not least, well, not even last, but one of the most important advantages, it's highly predictable non-sequential overlap for application of SLAM. And here I have to get into a little bit of detail. So let's go back to this SLAM thing. So this is a frame N. Okay, we know that. How the how we can find what's the number of a frame here which covers the same area? Because it's been a long time since it went that way, that way. How the hell we can do it? So I've been there. I've done that many times. That's how we do it. So this is the frame we choose. We decide. For some reason, we decide, oh, yeah, I've seen this somewhere else. And I want to find another frame which shows the same feature. And then you start watching video. Oops. Nope. Sorry. I clicked the wrong place. So you start watching video, and then you stop and say, okay, is it the same pattern or not? Maybe not. Keep watching. Oh, no. Keep watching. Well, it's going actually much, much faster than in reality. You can spend hours, you can spend weeks doing that. But eventually you will find something very specific. Typically it's like a boulder or specific algae or whatever, coral, I don't know. But here, how can you find it? You cannot. So what can we do? We'll take the original funny pattern and we say, this is frame 9, and this is frame 40. And most likely, they are covering the same area because they are close to each other. We don't know what's happening here because it's too distorted. But here we do know. So everyone, even sophomores, can do that, right? So let's look at the part of the result. So these are number of frames, and these are differences between numbers of frames. So it's all within, well, next slide will show it. So it's all within like 31, 32. So it's highly predictable. You don't have to think where you can find the non-sequential overlap. Once you found it, you are guaranteed to have it forever. With maybe some, well, you can probably stay with one, but then it will just travel away from the center. But you can correct from time to time. So for this project, there was filed the provisional patent, and we are waiting what is going to happen. And thank you. Thanks to Mike Tuttle, Jen, Tom Lipman, who gave me a very interesting insight, Carlo and Tom, who provided us with the motor and explanation how to use it. Questions? Yeah. Jennifer.
So did the heading of the arm determine your shutter speed or how fast the camera was taking images? Because you could vary the velocity of the whole platform, but you can also vary the camera.
Absolutely.
shot.
Yeah, and I've shown here a single estimate which expects certain shutter speed. But of course, if the more frames you take, the better the coverage. So we used GoPro, and from the original imagery that McLean took, I had to take every 20th frame, and the mosaic was done with this every 20th frame. I could have probably used every 40th,
yeah,
and the coverage will be slightly less, maybe twice less.
Could you use, like, depending on the heading of whatever way the arm, whatever arm, if you had multiple arms going, to determine when to take the photo?
I think that every situation can be easily simulated. So as soon as you start putting real numbers into the simulations, you can figure out what kind of what number of frames you need in a second or in a minute, how fast you should rotate, but it all depends on the circumstances. On the altitude, you remember all these parameters, on the camera altitude, on the length of the arms, on the rotational speed, on the camera parameters, where I used only this vertical field of view, but there is also horizontal field of view, which is also affecting it. So I had only a very, very rough estimate, which guarantees absence of gap. Jordan? Wait a minute, just a second.
Whenever you were recording data, did you have it set to the video settings and then you had it 30 frames per second and you were taking stills from it, or were you on the camera settings and it was continuously taking at a given interval?
Yeah, well, we just use it straight because it's better to have more than necessary than less than necessary. So subsample frames is easy. Do it repeat this experiment is a nightmare. So we used as many as we could. Because we were not restricted with the storage. You know, it was like few gigs every video. We were capturing video.
So was your patent for, the platform that would be going underwater or one that would be used in air?
In air, you have GPS. You don't need all this funny stuff.
Okay.
But it's only the absence of reliable navigation. And what I mean reliable navigation is a pixel size, pixel accuracy. Because if you use LBL or USBL, you know, what is that? So when you use that sort of navigation, you are like, you try to put together two images and they actually overlap, but the positioning system puts it like a couple of meters away. A couple of meters is nothing, but you cannot combine images which are a couple of meters away from each other. You cannot register them. So it's not the pixel level accuracy. Well?
Sorry, I was going to throw it to him.
It should be a boomerang. You know, you ask the question and then it returns back to Will.
Yeah.
Yuri, I could imagine that like the navigation, the SLAM navigation process could could work better or worse for a standard booster feeder pattern where the images are all overlapping, for example, in the forward direction or in the sort of orthogonal direction, relative to this method where the images are all kind of rotational with respect to each other. Do you have a sense of whether or not this method improves the SLAM solution or maybe
Of course it does. Of course it does. First of all, because to use SLAM on any other pattern, there is no predictability. You can only guess, and you have multiple guesses. You have one guess, then and if it works, if you actually got it right, then this pattern becomes more sensible, and then you make another guess. Oh, that must be close to each other. And then you, if it works again, it gets even better. And this is a very, very painful and slow process. Here, no problem whatsoever. You know you are guaranteed overlap between sequential frames, as in any survey, but also as soon as you figure out the first overlap between non-sequential, you just stay with it. Or maybe vary it, like one frame here, one frame there, or you can just adjust the rotational speed, and then it will be just 31 all over.
Thanks.
Yuri, is there a potential that this could cut down time for data collection and underwater camera mapping?
I'm sure it does. It has a great potential. The question is that not many people are happy with something rotating on their AUV, ASV, etc. But I think it's just the inertia of our mentality. As soon as they'll get used to this idea, so what's wrong with rotating disk, for example? Disk is working as a gyroscope. It actually adds the stability. So, and if we design this disk or arms with cameras in such a way that the drag is almost insignificant, it's no problem. It will be just rotating and increasing the swath.
Did you have any issues with blurry stills, or were you operating at a speed where that wasn't an issue?
There was practically no issue. I would say that the setup for GoPro was non-optimal. So everything was a little bit blurry. So because, you know, cameras have focus, certain distance within which things appear in focus. If you adjust it a little bit and stay within certain range of altitudes, then the quality will be much better.
Cool, thank you.
And I'm not going back there, right?
Okay, so this is pretty cool, but you're saying that no matter what area you're gonna try to swath, you're gonna just expand your arm length so that you don't have to double back on yourself?
Theoretically.
Okay, because you still technically, like if you had a large enough area, you're still gonna have to do your pseudo mow the lawn, right?
Okay, no, well, not necessarily. Imagine that you need the area, well, video survey is, well, 100 meters by 100 meters, right? So if you have 100 meters long arms, then...
But that's not really practical.
It's not practical, no.
So
I agree with that.
how do you fill the gaps when you do have to
You
apply the
don't.
log method?
Well, that's what I said. It relaxes these constraints because the swath is so wide that you don't really care if it overlaps less or more. Only when you are have very narrow swath, as in the example, then you have to be very careful about going back.
Oh, because you're saying because you have such a large swath that you're not gonna.
Right.
mess
Yeah,
up.
you don't care because it's well within the accuracy of LBL or USBL.
Thank you.
Hey, Yuri. So when you were showing the two sets of solutions, initially you had like a concentric thing happening with the path with the first solution, and then with the rings with the flight line. And then you were able to get the solution like this after. And you showed some, like I guess a cross line, I think
Yeah,
you were calling
cross
them.
links. Yeah,
Cross
yeah,
links.
Yeah, okay.
So was that from the single swath going forward, you were able to get those cross links, or did you have to go over it another time?
Well, when you are processing imagery, first of all, you start with the registration of sequential frames because you know that they have overlap.
Yeah.
And that's what, that's when you do that, you end up with this funny pattern because of some obliqueness of the camera.
Yeah.
So, but when you start adding crosslinks, then the errors which are accumulated over this long run are redistributed in such a way that the pattern becomes sensible, sane.
So is that like finding the non-sequential
Yes,
overlaps? That's all
yes,
it is? Okay,
yes.
great. Thank you.
And that is the idea of the slum. So slum started with the small robot which goes within a building and it looks everywhere and it says, okay, I saw wheel here. I returned back here and wheel is still here, so I've been here, so I can redistribute the errors which are accumulated. And they don't care if wheel went someplace else. Well, but of course there are more reliable features than wheel, like watch, this or whatever, exit. Yeah, it's there always. So that helps to build build the slum solution and redistribute the errors in the optimal sense. Wheeler, you wanted to ask something.
Yeah, she actually asked the question I was going to ask, so we're good, thank you.
Oh, okay. So nobody wants to do the experiment to help me, huh? We always need help. Okay, got it.
So there wouldn't be any advantage to just driving your boat in these big
Yes.
circles?
Yes, it's the same, essentially the same. And actually, that was the original idea. I was thinking that what if we take the ROV and just make it move a little bit every time when it's rotating? Easy. Yeah, you can do that. It will essentially will be the same. And it's easy to program, I guess. But then I thought that this solution is actually easier because you have something bulky, which moves only linearly, and you have something rotating, which is not affecting its movement that significantly.
I wonder actually if it is the same, because I wonder if the advantage that you get in this scenario is that you're running with a fixed lever arm, like radius. And so the overlap from those images, it constrains the motion in that sense. And if you were driving in circles without a fixed arm, you still have a navigational error that could cause gaps along the way.
You might, yes, but I guess you can prevent it. And anyway, if you have rotational arms, but you are moving too fast, then you will have gaps in the middle. So that's why you have to stay below certain linear speed to guarantee. It doesn't mean that you may not have gaps even if you are moving faster, but this, at least, it's a lower bound. Jordan.
So this is for the actual experiments. In one of your slides, you showed if you're moving a constant speed forward linearly, you have a different amount of coverage depending on how fast the arm was swinging around. And since you did a lot of the actual experiments, I was curious, given the size or like the length of the arm and the settings for the camera, did you find that there was like a maximum and minimum speed that you could do to get good data?
Yeah, I was working on optimization, and really, it doesn't hurt to go as slow as possible linearly and as fast as possible rotationally.
Okay.
So honestly, that's the optimization: as slow as you can linearly and as fast as. But I didn't want to break anything, so yeah. I mean, the bridge I'd run as slow as possible, like 0.01, like 0.001 meters per second.
Okay.
So yeah.
Do you have an idea of like what the rotational speed was though?
Oh yeah, it was about 6 revolutions per minute, I think, was what we did in this experiment. I've done some at 8 revolutions per minute, but we used 6 for the final.
And then the length of the arm, because that's kind of dependent.
That was about, my arm's like 6 feet.
Okay.
Yeah.
Yeah, I have to say, that the processed imagery was only from one camera. And the reason is we could double it. Yeah, but it didn't make sense because our wave tank is too narrow for our experiment. It didn't make sense to use 2. But it's all intertwined, all these parameters, and it's only simulation can give you a certain answer.
Any more questions?
Christos wants to ask that if I'm using boustrophedonic correctly.
We don't use it.
I was a little bit nervous because I have no idea how to pronounce this word. Yes. But in fact, it came from the reading and writing, because some are writing from left to right, some from up to down, and this boustrophedonic writing is like that. Funny people. But for me, it's just lawnmower.